Yeah, so my name's Paddy Cullen. I'm a senior lecturer at the School of Engineering and Materials Science at Queen Mary University. And my research, so I guess my first degree is in chemistry, did my PhD in physics, and I've been working chemical engineering for the last 4 or 5 years. So yeah, you can tell by that it's already quite a cross-disciplinary discipline itself, chemical engineering. And as you'll see, I think from the presentation I'm about to give, my research group, so I teach and I research. So I'll be teaching some of the modules that you'll go on to study if you come to, when you arrive to do chemical engineering, Queen Mary. And I also research, so I've got a research group of around 7 PhD students, and they are looking into, a lot of what they're looking into is trying to make batteries better. So that's about making new materials for batteries, but then there's also things that I do that are more chemical engineering. So batteries are chemical engineering because they're very complicated, but more traditional chemical engineering stuff, such as designing new catalysts for different reactions and things like that. So that's me.
Before you get started, should we do a little bit of interactivity with our attendees? So if people would be able to write in the chat just to let us know where they're from today. Are you from the UK or are you from another country overseas? If you feel comfortable doing so, of course.
Yeah, we can give you a few minutes or a minute.
So someone has said England, unsurprisingly. Is there anyone from anywhere further afield than England? We're not getting anything, so I'm going to assume you're all England-based students. If you do want to let us know that you're from somewhere else, feel free to write in the chat, but it's interesting just to see who we have in the room and where you're from in the virtual room.
Okay, shall I crack on then, Holly?
Yes, please.
Okay, so let me share my screen. Here's this one here. And here's my presentation. Hope that's looking good, Holly. If you give me the thumbs up, yeah?
We can see.
Right, okay, cool. So as I said, my name is Dr. Paddy Cullen, and I am senior lecturer in Queen Mary School of Engineering and Materials Science. And I'm going to talk to you today about chemical engineering and why you want to study it, what it is, and what it can lead to. So first of all, maybe I can just minimize this. First of all, this is Queen Mary. This is the Queen's Building. And chemical engineering sits within the School of Engineering and Material Science. So we'll learn about that. Why chemical engineering is a good subject to study, what's it about, what we'll teach you, people's research, such as mine and a few others, some careers that can come out of doing chemical engineering, and some more details. So that's the structure of today. Now, I need to move things around, close that. So at the top here, we have Queen Mary, and then we have these different faculties underneath. So Queen Mary is a university which has multiple different subjects. So it's not a completely science or completely medical university. There's humanities and social sciences in there. So people studying history, English, politics, whatever you can imagine in humanities. But we are the Science and Engineering Department, and there are, faculty, and there are these 5 different schools there. And in SEMS, which is the School of Engineering and Material Science, we have these 7 different streams. And so here we're going to be talking about chemical engineering today. In our School of Material Science, you've got many different labs. You've got chemistry labs, you've got a chemical engineering lab, which is specific for this stream. We also have different labs which are very useful for chemical engineering, such as the fluids lab and the heat transfer lab. We have this newly renovated in the last 5 years, this huge room, which is very useful actually for Chem-Eng, because this is a sort of triple height room. If you see here, like there's a large headspace above it, which means we've got a fixed bed reactor that fits in here, and that is specifically for some chemical engineering labs. And it is, I think it's just over, it's 3 meters tall, I think. So that wouldn't fit in a normal room. So it's quite useful that we have this lab for you to use as Chem-Eng students. And yeah, this is a room exclusively for undergraduate teaching. You can see here there's these little tables, people doing group work around the tables. Sometimes they'll be doing group work and following some instructions on these screens on the computers. And so it's just a nice space in which to learn this new place. And here we have another look at it. Here you can see the large headspace there. So why chemical engineering? What is it about? So as I said in my introduction, it's very interdisciplinary. So I said I've got a degree in chemistry and a degree in physics, and then there's also process and computational engineering involved. So chemical engineering really sits at the intersection at a lot of these different fields. If you're interested in earning potential, the chemical engineering starting salary is quite high when compared to all other UK undergraduates. There is a steady demand for it, and there is lots of things you can do with sort of degree: consultancy, work in power, waste, and beyond. Okay. So what is chemical engineering compared with chemistry? So one of the answers is that chemists do reactions in a flask, but chemical engineers do reactions to make huge amounts of compounds. They have to make sure that the processes are energy efficient and are safe, they don't explode. So I would, in my chemistry days, have made maybe micrograms of a material, whereas chemical engineers take this process that I've made to make micrograms and do, kilograms per minute, that sort of scale of things. So any of these things you've used, pastes, foams, creams, soaps, perfumes, ceramics, alloys, all of this the process would have been made by a chemical engineer. So if you look here, you'll see loads of different materials in this little picture, and all of them actually have been made by chemical engineers. So the toothpaste itself, what you want there is a material that is solid but is liquid when it moves. The container will be made by chemical engineers. This brush would have been made, the process to make this brush would have been made by chemical engineers. And the handle and the actual brushes themselves would have been made by chemical engineers. So all of these products include a lot of chemical engineering. And of course, this is what we call the life cycle analysis. So as well as making these materials, we need to make sure that we are not wasting lots of energy or contributing to the demise of the environment. We want to minimize carbon dioxide costs and also dollar or pound or whatever currency costs in our processes. And this is something we would consider whilst teaching chemical engineering. So there is a whole module on life cycle assessment, which tells you about how to count up the carbon cost of your process. And a lot of what you learn will be about optimizing your process and making engineering decisions in order to have the lowest carbon cost and the lowest dollar or pound cost or whatever currency cost of your process. So what we will teach you, and I'll go through this now. This is a typical week, and don't be scared about all of this green. So we have lectures in blue, so you'll have this many lectures. There are some support sessions, so I have advisees or personal tutees, and I would meet them every couple of weeks to check in, and we all meet together and chat about what's going on this week in the course. So that means people can stay on top of things, or they can book in one-on-one sessions with me to see, to talk about whether, if they're struggling with their academics, I can try and help them out, or if they need some advice on anything, I can help them out. And there are some problem-solving classes. With the green labs, I would say they're not this common. What you might have is maybe 4 blocks a week, but because but they may change every week, or every 2 weeks generally, because we might have one group in here and then one group on the Tuesday and then one group on part of Thursday and Friday, for example. So it'll be split up a bit into groups for the labs. And then on Wednesday afternoons, this is nationwide. There's no teaching that takes place at universities in the UK, so that you can get involved with students' union activities. And they can range from things like sports or hobbies or, different sort of volunteering schemes. But there's something for everyone generally in the Students' Union. So in year 1, what we have in year 1 is a core engineering skills that many engineers need. So year 1 is actually in common with a lot of the other streams, which you have seen earlier. So the other streams would be aeronautical engineering, materials engineering, biomedical engineering, mechanical engineering. You'll be in the same lecture hall as some of those students for some of these modules, just because there is core engineering skills and knowledge that everyone needs. So in the first year, it's more common, and then as you go up the years, you'll see it gets more and more chemical engineering specific for this course. So we have experimental design and practice in 2 terms, which are, very core engineering knowledge and skills that you need to learn. Computational and mathematical modeling, engineering design, materials engineering. And then we have fluid dynamics and thermodynamics. I teach the materials chemistry course, so that has all the streams apart from mechanical engineering and aeronautical engineering. So in this course, for example, you'd be chemical engineers, biomedical engineers, materials engineers, and sustainable energy engineers. And finally, you do a bit of specific module on chemical engineering here. And so you do start getting specific from the first year, but as you see, it will get more and more specific as we go on. Talking about these in a bit more detail, this is from the chemistry side of things that I teach. So the chemistry module goes from individual atoms, even subatomic particles, all the way up through molecules and reactions to things like band theory and why things conduct and why things insulate. And then we have some classic sort of thermodynamics in here that everyone needs to know, as well as things to do with reaction constants. And we don't only, it's not maybe what you might have seen in films or popular culture, how university is taught nowadays. When I was taught, it was always not that long ago, maybe 20 years ago, well, 15 years ago, there's always a lecturer at the board with a piece of chalk or whiteboard with a pen. But now we teach very, I think, much more engaging way. And so there's a lot of self-studying, which is a large part of university. It's like learning how to learn. That's a large part of why university is important. So that when you go on after university, you want to learn something else, you know the way personally for you that how you go about learning things. And that's different for everyone. And that's a very interesting part of the journey. There's also learning how to work in a team and manage group projects. If you're a chemical engineer, you're never going to be working on your own. If you're an engineer, you're never going to be working on your own, whatever type of engineer. So being able to work within a team and manage group projects, maybe even with people who are not like you or who you don't know very well, and sometimes maybe you don't like, these are the challenges that you need to get over. If you're working for a large or small, medium-sized company after your degree, you need to be able to work with colleagues, no matter who they are. And often these high-level jobs, they're very international, people from lots of different cultures. You'll be learning communication skills, whether that be learning how to talk to different audiences at different levels. So you might have to, for example, present one of your group's work to professors, or you might need to present your work to people in the years below you. And that requires editing what you say, how you communicate things in order to suit them to different audiences. As well as, being able to communicate with your peers to get these projects done. And there's a lot of problem solving that we'll be going through as well. In year 2, now we're getting a bit more chemical engineering specific. So unit operations, process control, applied fluid mechanics, phase transformations, process design and simulation, heat and mass transfer, chemical reaction engineering, and separation processes. So most of these to me look like actual classic chemical engineering modules. So for example, separation processes might be something like you have a water treatment plant, or you have got a recycling plant, for example, and you want to separate all the metals from all of the plastics. How would you go about doing that in your stream? You might have 5 different types of plastic. How would you then go about separating all these plastics out? Chemical reaction engineering, you might be working for a big pharmaceutical company and you need to, someone in a lab somewhere has made a new molecule, like a target molecule, which would be great for curing some disease. But now, instead of having a gram, you need to have 100 kilograms of it so you can sell it and save lives. And this is kind of the module that would teach you how to do that. So here is a big sort of chemical plant. And then, yeah, there's also, we do courseworks. And so there is a sort of variety of different courseworks done by different students. And so this one was done on different waves. And the applications of this is in mixing emulsions, jet stability, and coatings, for example. And you can see that they've done some coding to sort of look at the velocity map of different waves across this barrier. Here's another one, which is looking at a tubular reactor, where we have this reaction A going to B going to C. And you start here with a lot of A and no C, which is your final product. And maybe this is heated, for example. You heat A, it gets turned into B gradually, and then as A goes down, B goes up, and then B turns into C. And so this batch reactor, this is a type of reactor, is something that someone has modeled here. And it's important to get this right, because you don't want the... so they've modeled it here to get this graph out. And if you get this graph the wrong way around, you might have something like, actually, okay, we don't want C and A in too much at the same time, because otherwise we'll have a problem. So you need to get the heat gradient across this tubular reactor right. Okay, so that's an example of modeling a reaction in order to get the desired products and safely. Another one, or this is another one, which is another reactor design coursework where people are trying to, what they're doing is a batch process here, which is to take sugar and some cells. They want to grow these cells, and they want to make these cells make this actual medicine. So this is their metabolic products. So the cells will replicate themselves with the sugar, and also they'll produce these products, these anti-cancer medicines that you want. But if you were to put in loads of sugar at once, you might have a spike in the cell population, which might drop very quickly. So you want to be able to have the right amount of sugar. Maybe you find out here, actually, this is where we need to put more sugar in, or we need to drop sugar in constantly at this level. And by modeling this process here, you can maximize the amount of anti-cancer medicine cells produce and minimize the amount of sugar you put in. That's the sort of chemical engineering modeling that's being done here. Moving on to year 3, there is this integrated chemical engineering design project, which is spread over both terms. You haven't seen that before. This is a long project and it's worth double credit. And what happens in that is you're assigned a chemical engineering project. So I've run one. I know some of my friends have run one. So colleagues have run a lot. So an example of this would be to get all of your chemical engineering knowledge so far and be able to tie it all together for a specific brief. And I, for example, would be the client, and you and your group would have to come up with, I'm saying, okay, I want to build a water waste treatment plant, and I want to invest in that. You need to convince me that your engineering proposition and your business proposition is convincing for me to invest in it. And you'll be given so you'll say, okay, we want to build this water treatment plant. I want to have 10,000, well, maybe 10,000 liters of water clean every day out of it. And I want to, where do I locate it? Where's the best market opportunity? I want you to tell me about the safety aspects. You need to design the whole water plant down to individual parts of the water plant, and you need to do all the safety. You need to do a business plan. And yeah, that's an example of one of these projects, and you'll see some more later on. But that's a really interesting module, I think, because it really ties together a lot of the concepts into one large module. We also learn about fuels and sustainability, catalysis, reaction design, process safety and loss prevention, very interesting and important. Safety, you can get huge explosions, as you well know, probably, from these chemical plants. Heat exchange and waste minimization, very important for minimizing your carbon emission and also maybe the emissions waste of your initial reagents and costs. Sustainability assessment for design. So this is about teaching you how to look into how sustainable each of the parts of your, for example, water treatment plant are, and electrochemical engineering and energy storage, which I teach, and that is about so we cover batteries, we cover supercapacitors, and that's another type of energy storage. We look at the hydrogen economy and using hydrogen as a fuel, as well as going from batteries, small batteries that you'd see every day, to getting batteries into the grid to enable renewable energy, for example. So let's keep going. Yeah, these are two examples. I talked about the drinking water plant for the third year design project. Another one run by Paul Balcom was a zero carbon ammonia for shipping fuel. So shipping fuel is quite dirty, very fossil fuel heavy, and like kind of, yeah, the not very clean fossil fuels either. It's low grade fossil fuels. So oil, basically, or like low grade oil. So what we can do is possibly design boats to run on ammonia instead. And the aim of this project is to design this boat and a system around this boat in order to fuel it with ammonia made in a zero carbon way. So that's another example of one of these projects. This is a group project. You wouldn't have to design everything, but if you look at these, okay, if your project was this, like if you could split your project into this sort of rectangle here, you would have to design 1/6 of this whole thing. So one of these boxes, for example. In year 4, for MEng, there is some other modules as a research project. Again, we have some modules, a few different modules you can go for as well: renewable energy sources, advanced gas turbines, advanced polymer synthesis, whole system design and sustainable engineering, for example. And we have, you get to choose 2 out of these 7 different modules, for example. And for MEng, you need to actually do original research. So it can't be, or design, can't be anything that's been done before. So we try and get you to do something completely novel. So I'm getting towards the end now. I'm at 5:30. So this is an example of some of the research that's going on. This is Joe Briscoe's work, professor at Queen Mary. And he's made this process to try and what it does is, it's called aerosol assisted chemical vapor deposition. What he does is he takes solar cells in here, and one of the applications is to use ultrasound to take this fluid here, make a mist, and then pass this gas over some old solar cells, and this is heated. And in this reactor, you can reform solar cells to make them more efficient. So it's about recycling solar cells as one of his projects, for example. And yeah, I don't know. Yeah, here Joe has, a project student has modeled the flow of gases or mist from the original where the ultrasound turns the liquid into mist through the reactor and over the actual solar cells, for example. I think that's done. This is Edo's work, and he's looking at nanostructured materials, and they have to be electroactive, so they need to be conducting and porous, and not only do they have to be porous, but you need to have pores that are interconnected. So this here on the right, this is X-ray CT, so that's X-ray computational tomography. So this is basically a CAT scan, which is a medical thing, of a material. And what you can do is you can do an X-ray through this material, take many X-rays all the way around a material, and then use a computer to make a 3D reconstruction of the material. And then afterwards, you can map if a fluid could go all the way through this material. So here you see, I think this red bit here might represent an unconnected sort of pore, whereas this blue bit, liquid could go all the way through these pores. So these sort of materials are important for catalysis, batteries, gas storage, gas separation, all of these different applications. Another one, I'll just have a look at the time, 7:33. Another application is, this is Anna Sabrido, who makes these, it's called electrospun fibers. And these are, she ends up with these papers of carbon, which are conductive and really porous. So this is a sort of zoom in of this material here. And this is 1 micron. You can see that these are less than a micron. So this is probably, I don't know, a fifth of a micron, which is 200 nanometers. And just to give you an idea of scale, a human hair, I think, is about 50 microns to 100 microns. So these are a lot thinner than human hairs. They're probably 250 times thinner than a human hair, and they're conductive. So these can be used in a lot of different applications, including batteries and supercapacitors. This is an example of Zhi Zhang's work, and he looks at alternative fuels for combustion engines. So combustion engines sound like a thing of the past, but they're still very important. If you use gases like hydrogen, which can be produced in a green way, then you can still have combustion engines which are zero carbon. But these come with different problems. Yeah, with hydrogen relative to hydrocarbons, you have problems like turbulent mixing and combustion near the walls. And Xi does a lot of work to model these types of combustion and using a computer, and then compare it with experiments. There's me. I make nanomaterials, put them into batteries and things like supercapacitors, and this is a hydrogen fuel cell. These are different devices I make in my lab. And then finally, careers. These are lots of different types of companies you can work for. And I think we've had students go to all of these different companies. Here are some stats with graduate salaries, and these are a couple of years old now, these stats, so I would probably look these up. There's a good website called Grad Cracker. You can look up these opportunities on, so I guess you could go on there and see what the salaries look like now. But you can see here, this is from 2018, so I would have a quick look, but I imagine the salaries have gone up even more since then, and they're 20% higher than the average UK graduate still. Here are some figures I pulled out of a report. I think it was by the National Grid. But you can see there's a lot of advantages to doing an engineering degree or chemical engineering. And a big one is that we just need a lot more engineers every year. We're not meeting the amount of engineers per year that we need, the amount of graduates we need every year. Engineering is obviously very valuable to the UK and whatever country you're from. And yeah, you have a higher salary on average, and it's a growing industry. We need it. And I think that's it from me. There is some stuff on accommodation. If this is true of all Queen Mary, you are guaranteed a spot if your home address is outside of Greater London. Guaranteed a spot. In the student halls. If your home address is outside of Greater London. But apart from that, you can stay at home or rent or do whatever you like. And I'm going to stop sharing now and take some questions because I know slightly overrun.
No problem at all. And just to add, for the last couple of years, Queen Mary has been able to guarantee accommodation to all first years who apply by the deadline, which is normally at the end of June. So even those who live in London have been able to get a place in accommodation as long as they adhere to the deadlines. So that's positive news if you want to live in accommodation. Shall we start our Q&A?
Yes.
Does anyone have any questions for myself or Paddy? If you want to write them in the chat or the Q&A button, please do so now.
And maybe we'll give you a couple of minutes to do that. How was that, Holly? Do you think that was okay?
I think that was great. As someone who knows nothing about chemical engineering, I have a much better understanding of what it is now.
Okay, good. That was part of the aim. So yeah. The thing is that, even at at secondary school or college, people don't know what chemical engineering is because it's not taught at school. There's no A level for chemical engineering. So explaining what that is, I think, was part of my goals, I guess, for this, my objectives. Maybe we'll give another minute for chat.
I think that's a good idea. So while we're waiting, I will just plug our open day, which is coming up on Saturday next week. So the 7th of October, we're going to be having an open day on campus in Mile End. So if you want to come down and have a look at our facilities, we'll have student ambassadors running tours, and you'll also be able to talk to academics like Paddy if you are considering other areas of engineering as well. So you can still sign up to that. If you search for the Queen Mary website, you will be able to book onto the open day and come and see us. We have had a question. So this one is for you, Paddy. In year one, semester one, what would computational and mathematical modelling consist of? So any more detail you can add on that would be great.
Okay, yeah, sure. So I think that one, I don't teach that one, but I think that one we look to do a bit of Python in there. So there is a bit of computation in there. And a mathematical modeling that might meet. I think that's because in year one it's general, right? As I said before, it's across all of the streams. So as in it's like materials engineers, chemical engineers, aeronautical engineers. So it's just general modeling at that stage. So learning the base skills you need. And then when you get into the years above, you'll use those skills to solve actual chemical engineering problems. So it's kind of a general course on that before you go to apply that to chemical engineering later.
Thank you. And then this one is a bit more about the admission side. So I'll probably take it.
Okay.
So this person has asked, could we learn a bit more about contextual offers for engineering? So generally in the university, we have the same policy for contextual offers on the majority of programs. So what a contextual offer is that if you meet certain widening participation criteria, you might be made an offer with one grade lower than what we show on our website. This is to encourage people from underrepresented backgrounds in higher education to be able to come and study with us. So I will just share screen because we have a really helpful webpage all about it. And there's also a new tool where you can calculate whether you would get a contextual offer. Let me just see if I have the ability to screen share. I'm not sure that I do.
You could send it to me and I can screen share if you don't.
That's a great idea. I will post the link in the chat anyway, so people can navigate to it themselves.
Okay. Do you want me to share it? Or
yes, please, if you wouldn't mind.
just give me a sec. Okay. So I will share the screen now.
Thank you. So, like I said, it has some information about who would be considered for contextual offers, as we know that some circumstances can affect your grades and may kind of affect students being able to achieve the highest grades. So we do make an allowance for that. There's some kind of HE jargon here as to what is considered for a contextual offer, but what I think will be more helpful to the people on this call is the contextual calculator button at the top.
Shall I press it?
Yes, please. So this is new. I've not actually seen this before, but if you answer a few questions, such as putting your postcode in, putting your school in, and signifying whether you've been in care or if you've done one of our access programs, then it should be able to tell you whether you're likely to get a contextual offer or not. So it's dependent on a few different things, such as the area you live and how many people go to uni from that area, your school, how many people typically go to uni from your school, and then personal stuff, such as if you've been in care, etc., as that decreases your likelihood of going to university. And we're trying to make sure that's not the case.
Right. I didn't know about that. That's really useful and interesting to know about.
So we have another question about chemical engineering. Will not specifically naming it in your personal statement hinder your application? So I imagine this person's applying for different types of engineering courses.
I don't have, and I don't read. I'm not a very good person to answer that, I'm afraid. Just because I'm not a UCAS reviewer, I've never done that, so I'm not sure. Do you have an answer for that?
I think it would be okay to keep it generalized from the academics I've seen advising our applicants. Generally, if you have the grades and the subjects that we're looking for, you will be made an offer.
If you just keep it engineering general, that's fine, right?
Yeah.
The message, yeah.
Yeah, I think there would be quite a lot of students who are potentially applying for different types of engineering, and we will just look at your grades and how well that qualifies you to do the course. So I wouldn't worry too much about not making the whole thing really specialised to chemical engineering. I hope that helps somewhat. But at our open day, if you do want to come, there'll be different academics who probably would be the people that would be looking at your personal statement who might be able to give further advice.
And when's the open day?
It is on the 7th of October, next Saturday, on campus here in Mile End, East London. So that's the end of our questions that I've received.
Great.
Unless anyone's holding back on any questions. We do have a question actually, and it's about the entry requirements. So I have maths and chemistry, assuming that's A level, no physics. Do I meet the subject criteria? Paddy, do you know? If not, I can check the course page quickly.
So I've got the course page here. I can share it. So, okay, just to give you context, I just searched for Queen Mary chemical engineering. And so this is what comes up, Queen Mary chemical engineering. And what you can do is you can go down to here, and there is these different menus that helps you skip down. Entry requirements is one here, so you'll just scan down now. And there's chemical engineering here, all these different versions of the chemical engineering course, and it's quite easy to switch between the different BEngs, for example. So if you want to do a year with industrial experience, you can apply for that, or you can just apply for this and then change to these different courses after year 2, for example. If we look at ChemEng here, we've got AAB at A level, including maths. So you need to have maths and either physics or chemistry, it looks like. And you can't, this AAB excludes general studies and critical thinking. So that for A level, this is the criteria. So you need maths and either physics or chemistry.
So based on what you've said, you would meet the entry requirements for subjects.
Yeah. And you can see all the different, if you're doing international baccalaureate, you can see the different entrance criteria here as well.
Would you mind scrolling? I'm really sorry, because there was a contextual section there, which I haven't seen. So it might actually have the grade for contextual.
Was that down here? Okay, here we go. Yeah. So it's the same, except ABB instead of AAB, right?
Yeah. So you may be made an offer of ABB if you meet one of those contextual criterias, or there's actually a BBB one, which I think is for people who've done one of our access to university programs. So that actually shows you what the contextual offer is for this course.
Great. I'll stop sharing again. And we'll give it another 20 seconds, but I think we are probably out of questions if they haven't typed it in by now. So Holly, I'm guessing I'll see you on Saturday week. I'll see you on Saturday the 7th.
Yes, we'll be here all day, running the engineering activities and talks. And in the meantime, if students want to go anywhere to ask questions, you can go to Unibuddy, which is a platform where we have lots of different student ambassadors from different courses that you can direct message with. They need to respond within 48 hours. So if you would like to talk to a current student online, maybe you can't get to the open day next week, or you want to just have a chat beforehand, you can head to Unibuddy for Queen Mary and start a chat with our students.
And do you have a link for that, Holly?
I do. 1 second. I've lost all my bookmarks because I got a new laptop. So I'm going the manual route. So I'll just post the Unibuddy platform here. And as you can see, there's different subject areas. You can choose engineering and material science. And we have 2 students currently who are working on there, but we're also recruiting some more, I believe, as we've just had a new intake of students. So I think you can expect some extras to be added on.
Cool. Okay, thanks very much, Holly. And thanks everyone for listening.
Thank you. We hope you found that helpful, and we will be sending the recording out afterwards if you joined late. So you will be emailed the full recording of our talk today.
Great. All right. Thanks, everyone.
Thank you. Have good evenings.
Bye.